Okay. Good morning, everybody. So I just put here where we stopped yesterday. So just remind to apply the semi-classical calculation, the semi-classical description, you need to fulfill the broadband condition, which tells you that the recoil energy is much smaller than the energy associated with the natural line width. And a consequence of that is that the time necessary for the internal variables to reach equilibrium is much smaller than the external time. So we make a calculation for the force operator, and from that we concentrate on the mean force for an atom at rest, and we end up with an expression like this one, where you have two parts. One is the derivative of the Rabi frequency, and the other part is proportional to the derivative of the phase. And the coefficients are just the real part and the imaginary part of the off-diagonal elements of the atomic matrix density. So, no, it's okay. So this operator is just you have in the diagonal the population of the ground state and of the excited state, and the off-diagonal elements are the two optical coherence between the ground state and the optical state. So the diagonal terms are real quantities, and you have two complex quantity in the off-diagonal terms. But fortunately, the sum of the two populations is just constant, and the two off-diagonal elements are just conjugate one of the other. And we write the master equation, which is just d sigma dt equal 1 over h bar. You have the atomic and the coupling with the laser, and the commutator with sigma. And we just add something which is related to the relaxation, which is in fact related to the coupling with the reservoir. And this term, just write, if I just the population of the upper state decay just as with the rate gamma, and it, as the sum is constant, it obviously is equal to the derivative of the population of the ground state. And so, sorry for the relaxation. And the off-diagonal terms just evolves. Just 1/2, and you can write that, deduce that from a Lindblad form. Maybe you will do that? No? Okay.
Okay. If you do it, I don't need to.
No, I will not do it. I was just mentioning that it can be found with the Lindblad form. You just have to the operator is just the raising or the lowering operator in the good position, and you just turn the crank, and it turns out, the factor of 2 turns out also. So, obviously the difficult quantity to calculate is this one. And so if you do all the calculation, it is not difficult. It is just lengthy. So I just give you the what I have found, and I hope I did not mistake. And so this is the usual, the one, the relaxation term, and then you have a term coming from the coupling, and obviously I did not mention here. I will take only the resonant part, and I have minus a omega 1 divided by 2 times sigma GA exponential omega L T plus phi of R minus sigma EG exponential I omega L T plus phi of R, no, small r. And that's it. And for, no, there is, what did I do? Just wait. Yes. And for this coherence, you have a free evolution, which is omega 0, and you have the decay, which is gamma divided by 2, sigma GE. And you have one term that comes from here, which writes omega 1 divided by 2 times sigma GG minus sigma EE, and you have exponential I omega L T plus P of R. Okay, at that point, it is interesting to note that if you consider the non-resonant term, in fact, it will change the sign. This minus becomes a plus, this plus becomes a minus, and so here probably, no, here, and here also you have a minus instead of a plus. And what will turn out if you just make the calculation as a perturbation. So for if you do not have any field, then the solution is trivial. You have all the population in the ground state, which is GD equal 1. You have no population in the excited state, and the coherence is 0 also. So this is a very simple way to make the calculation and to see the effect of the non-resonance term respect to the resonant one. And so, in fact, if you just look at the first order, you see that here what will appear for the resonant term is, as usual, omega L minus omega 0, because you are looking, this one is 1, and this is the perturbation, so you just have to solve this. And so you see this factor, obviously minus E gamma divided by 2, while for the non-resonant term, you change the sign here, and so it is a huge factor, because you have 5 or 6 orders of magnitude between the detuning and the optical frequency. So this shows once again that in the optical domain, for the usual conditions, you are allowed to make the rotating wave approximation and just drop the non-resonant term. Okay. So I just erase the red marks. And we go on. At that point, we want to have, you have two differential equations. And if you do not have the field, the coupling between them, then you just have something that goes to zero. Everything goes to zero with a rate, a typical rate, which is gamma, or gamma divided by 2, but it is gamma anyhow. And so we are not interested in what occurs in a time related to gamma minus 1, which is the internal time, because we are interested in the motion of the atom. So the typical time we are interested in is the external time. And so what the transient behavior of the solution we are looking for is not of any interest for us. And so what we are looking for, in fact, is only the stationary solution or state, steady state. And so we will try to find out. So I note sigma EE stationary, which is nothing else that the W stationary plus 1/2, because it is this difference, and you have the sum of these two, which is 1. And I am looking for the stationary value, which U stationary plus I V stationary times exponential I omega L T. So this is just because the forcing term is at frequency omega L. So I have to look for a solution where you have the same dependence for this term. And so I just postulate this form, and I transform these equations, which are differential equations, just in a system of linear equation, which just writes gamma divided by 2 US plus delta V stationary. The second one is gamma divided by 2 V stationary, minus delta U stationary minus omega 1 W. And the last one is so I think you can recognize them. So this one comes from the real part of this one. The second one comes from the imaginary part of this one. And you have an extra term that comes from this, which is written here. And the last one is just a way, this is the imaginary part, so this is just V. So at that point, you just have to turn the crank and express whatever you want as a function of whatever you want. And you end up with the stationary value, which is U stationary 2 delta gamma. And W stationary is, no, sorry, what I am interested in is W stationary plus 1/2, which is sigma EE stationary. And it is omega 1 squared divided by 4 delta squared plus 2 omega 1 squared plus gamma squared. So at that point, you just have to put these values here. And you can write again. So I just insist on the fact that this is the mean force, and assuming that we are not interested in the transient behavior. And so it is often convenient to introduce the saturation parameter, which is just omega 1 squared divided by 2 divided by delta squared plus gamma 2 divided by 4. If you come from nonlinear optics, very often this is written as the intensity divided by the saturation intensity, and you have 4 delta squared divided by gamma 2 plus 1. So it's just the same form, but for different community. And so the force just writes down as h bar, no, the h bar, I put it somewhere else. So the saturation intensity, the saturation parameter depends on the intensity, so it depends on the position. So the factor in front of it is S divided by 1 plus S, and you have h bar delta gradient of omega 1 divided by omega 1 plus h bar gamma divided by 2, and you have the gradient of phi of r. Okay. So if you make the same kind of calculation for the dipole of your atomic sample, then you find out that you have the same quantities U and V that comes into play, and the U is related to the component in the dipole which is in phase with the incoming field, while the V is in factor of the term that is in quadrature with the field. And as a result, you will have a relation between U and the real part of the index of refraction. So this is just a change in the phase of the field. And the V is related to the imaginary part of the index, which in other terms means the absorption. So the term that was proportional to the gradient of the phase was related to V, and so it is related to absorption. So this term is due to the absorption, and this term is more subtle, and we will call it the dipolar force. Okay, we now switch. We will look at each of the two components separately, because it is too difficult to treat them together. No, that's true. So, interpretation interpretation of the forces. And so the first part I will consider is the radiation pressure. And this one is the one which is easy. You just take hand-waving arguments and it comes out. The other one is more subtle. So this is the dissipative part, which comes from the gradient. So it is just minus h bar gamma divided by 2 s divided by 1 plus s, and you have the gradient of the phase. So the gradient of the phase doesn't mean a lot to us, so we will just consider a plane wave where you just have the phase which is minus kappa dot r, and so the gradient, so the laser, it is a laser. And so then you can rewrite the dissipative force as gamma divided by 2, s divided by 1 plus s, and you have h bar k. In fact, I just moved the h bar from here to there and change the interpretation. Because, in fact, this quantity s divided by 1 plus s was here. This is s divided by 1 plus s. And so you recognize here the population, the stationary population of the excited state. So at that point, the interpretation is almost immediate. You have some atoms that are excited. They fall to the ground state by emitting a photon. So this takes a time which is 2 gamma minus 1. And so this is the rate of emission of photons. But before the atom could emit a photon, he had to absorb a photon in the laser. And so this is also the rate of absorption of photon from the laser. And this is just the kick, the recall, that the atom will have to absorb when you have an absorption of a photon. So this is rather simple to evaluate. Sorry, this minus cancels this one. Change nothing, but the force is in the direction of the laser, obviously. So if you look at the dependence on detuning, this is on delta, you find that it is a Lorentzian, and so you have a maximum at resonance, and you have wings that goes down as delta to the power minus 2. So just one remark that I will make at that point. I can do it also later, but it is convenient. If here I have considered an atom at rest, if I have to consider an atom which is moving with a velocity, I will just have to change omega L to add the Doppler effect. And if I want to add a magnetic field, and I have a transition that is sensitive to the magnetic field, then I change the transition by a quantity which is just plus j mu b b, and as it is a frequency, I have to divide it by h bar. And as a result, in fact, for a moving atom in a magnetic field, the only thing I have to change is that I have to change my detuning, which is just the original detuning, and I subtract a quantity which is delta, and the small delta is k v minus, no plus, j mu b divided by h bar b. And this allows to use this radiation pressure force just to slow down a beam of atoms or of molecules. So it is a Zeeman slower, because as soon as you decelerate the atom, they are driven out of resonance because of the slowing down of the motion, and you compensate this change of the Doppler effect with a change in the magnetic field, and so you remain on resonance. And I don't know, but there is a poster. I don't know. No, I do not remember who was the girl in front of the poster, but there is a poster there where, so you just, okay, yes, sorry. So you go to see Maria, huh? Yeah. And you ask everything you want to know about the Zeeman slower if you are interested. Okay, now the second part is the dipole force. So it is the first term that was written here, and so it is dip. And what is nice with this quantity so if you turn back to the definition of S, you see that it is proportional to omega 1 squared. So you deduce immediately that the gradient of S divided by S is just twice the gradient of omega 1 divided by omega 1. And so you can express here everything as a function of S only. And so you have the dipolar force, which can be written as minus h bar delta divided by 2, and something which looks complicated but will be simpler, s divided by s. I just replace this by this. The factor of 2 is here. And so you immediately recognize that you have delta divided by 2, and you have the gradient of the log of 1 plus s. Which means that this force is conservative. It derivates from a potential, and you can write down the potential as u dip, the dipolar potential, which is h bar delta divided by 2 ln of 1 plus s. So, interestingly, you remember that the dissipative force was maximum at delta equals 0. Here, if you just put delta equals 0, then your force is equal to 0. Too bad. No, not too bad. So it changed sign with delta, and so, or here, so depends on what you are interested in, the potential or the force. For positive detuning, so when the laser frequency is higher than the transition frequency, then you have a force that will expel the atoms from the high intensity region. And obviously, if delta is negative, then you attract, expel maybe two L's. No, I don't know. It attracts the atom in the high intensity region. If you look at low saturation parameter, low saturation, which means either large detuning or low intensity, then, so in other words, you have omega 1, which is much smaller than delta, and eventually also gamma. Then everything becomes simpler. So if you just want to know the potential, it turns out to be h bar delta divided by 2, and you have just S as that remains. And if you want an explicit expression of that, it is h bar divided by 2, delta divided by delta squared, plus gamma squared divided by 4, and you have omega 1 squared divided by 2. And if you want the force, then the dipolar force is just proportional to gamma 2 divided by 2 in this limit. And it is a dispersive shape. And if you just consider now a standing wave, so in this case you can replace so the standing wave, you have just the gradient, which is equal to 2k. And if you just now calculate, in this case, the ratio of the dipolar force divided by the dissipative force, you find out that it is gamma delta divided by gamma, which means that if you go to sufficiently large detunings, the dipolar force will be stronger than the dissipative force. Okay, so this dissipative force can be, dipolar force can be used in different ways. One of the first use of the dipolar force for a blue detuned light was to make the bouncing of atoms at the surface of a reflecting prism. In fact, the situation was just to have an evanescent wave. It was a very beautiful experiment in the group of Jean Dalibard. You have a prism and you have a light laser beam that reflects in this way. And so here you have an evanescent wave with blue detuning, and you just drop atoms from above, and they cannot reach the surface, and they bounce, and they have seen 10 bouncing, 20 bouncing, which was very nice. So now it's also used as a beam to make a hole in a cloud, or make a dimple in to prepare a BEC, or it also has been used in the group of Jean Dalibard as a spoon to make the rotation, to induce the rotation of the BEC. So it is a nice use of this force. Okay, I think I will come back to the dipolar force when I will go to the subdoppler cooling, but for the moment, yes, maybe I can point out, maybe Jean-Michel will talk about this. This dipolar potential is related to the light shifts, and Jean-Michel will probably talk this afternoon about the light shift, which will be very useful for me because I will need the light shifts for the subdoppler cooling. Okay. We go on, and we just switch to the 3-level atoms. And the magneto-optical trap. So I assume that you know what is a magneto-optical trap, so you know that when I write MOT, I mean magneto-optical trap. Okay. So 3-level atoms, not we have to choose the scheme, and in fact we will choose a J equals 0 to the J equal 1 transition. And if you put a magnetic field, then you will move the levels, and you will have this shift in energy, or divided by h bar if you want. So this is the M equals 0, J equals 0. This is the J equal 1, and you have the M equal -1, 0, and +1 here. And on that you shine 2 lasers, one propagating in one direction and with the sigma plus polarization. And so in the frame of the atom, as the atom is moving, the frequency is shifted by the Doppler effect. And on the other transition, you have a sigma minus polarized light, and so it propagates in the opposite direction, and so the Doppler effect is just the opposite one. So I have mentioned it, just I erase it. You have 2 now. For each of these laser fields, you have 2 different detunings, which is minus or plus the small delta, with the small delta, which is just kV plus J mu B divided by h bar B. And if you have only one laser, it is fine. You know the result. We have already calculated it. It is the dissipative force, which is, so now you depends on the laser you are considering, gamma divided by 2. So this is for a single laser. And you have S plus or minus divided by 1 plus S, sorry, and h bar k. So this is just what we have calculated previously. But this is valid for a single beam. And you are not allowed to sum up the two contributions, because in fact, here you just take into account the saturation, so you take into account the depletion of the ground state. And so if you just consider that you have just one strong saturating transition, the effect is to deplete the population, which was all here. You put half of it in the upper state. And then if you just consider the second beam as a low intensity beam, so it is now saturated, it's instead of starting from a ground state population which is 1, you will only start from a ground state population which is 1/2. So the effect of the second beam is clearly affected by the presence of the first intense beam. So you are not allowed to sum up the two saturated forces. So you just have to go to the low intensity regime. So at that point, you have the dissipative force, yes, plus or minus, depending on the dissipative, always, which is, and you have only S plus or minus. And now, in this low intensity regime, I can sum up the two forces and just say that the total force, the total dissipative, is just F plus minus F minus. No plus, in fact, because they have opposite direction, but and at that point I can do everything I want. And if I now consider another limit, which is the low velocity and small magnetic field, then I have delta, which is much smaller than delta, and gamma. And I will make some expansion, because this S plus or minus is just omega plus or minus squared divided by 2 delta plus or minus squared gamma squared divided by 4. And so I will make some expansion in delta, the first order in delta, to have the friction force that comes out from the sum of these two forces. Okay, I have this guy, which I rewrite as minus plus delta squared plus gamma squared divided by 4. And I have to expand it, assuming that delta is small. So I have the main part, which is gamma squared divided by 4. And I have plus or minus 2 delta divided by delta squared plus gamma squared divided by 4 squared. So if you just assume yes, so this was in fact the point B, low intensity or observation. Do not remember if I had a A. No, I forgot to mention the A. Yes, the A. I was too fast. It was the 1D geometry. Okay, so we go on. So we assume that both lasers have the same intensity, because otherwise you have to carry on with omega plus, omega minus, and so you just call them omega 1. And the force, the two main parts just cancel because you have the opposite signs. So this one will not contribute. And the contribution is gamma omega 1 squared delta delta divided by delta squared plus gamma squared divided by 4 squared, and you have h bar k as a usual factor, and usually you write that as a friction coefficient time the velocity and a restoring a spring constant times the z, the position of the, so this is the friction and this is the spring. So the effect of that is to cool the atom, and this one brings them to the center of the cell where the magnetic field is 0. Yes, sorry. I forget to mention that I choose a magnetic field B, which is just linear in the Z component I am interested in. So you can write down now the friction coefficient as minus delta gamma omega 1 squared divided by delta squared plus gamma squared divided by 4 squared and h bar kl squared. So you see that when the detuning is negative, then the alpha is positive, which means that you have really damping of the velocity. You can see that the damping increases with the intensity, so it seems natural to have lasers with high intensity, but keep in mind that this expression is valid only when you can sum up the two forces, which means that you have to remain in the regime of low saturation, of low intensity. So it is nice to increase the intensity, but you are not allowed, or you will fall out of this approximation. So, okay. If you are interested, I will not make that in all the details, but I will give some hints to treat the high intensity regime. And in fact, I will change a little bit my point of view, and instead of calculating simply the force, the problem is that if I write the Hamiltonian in the rotating frame, and as now it is no, I always choose the ground state as a reference. So I have 0, I have an h bar in front of everything, and I have some couplings. So I generalize the Rabi frequencies so that I do not assume that they are real, because it means that I have to choose the phase properly to have a, and so I just keep a generalized Rabi frequency, which can be complex, and the usual Rabi frequency is just the norm of my complex. And I have also, so the problem is that when you have two different detunings here, it is not so easy to find out the stationary solution for that problem. Obviously, you can do one horrible thing, just plug this into Maple or Mathematica or whatever you want, and just say, okay, I want the stationary state. It works. You have 1 page, no, 10 pages of formulae, and you understand strictly nothing. So a more clever approach is to consider that what we are interested in, finally at the end, is just the linear part of the force when you consider that the small delta is a small parameter. And if you consider that delta is a small parameter, then you will have all the machinery of perturbation theory which allows you to jump in the problem with pleasure. And so you split the Hamiltonian. H, I just write it is a 0 part plus first order. And what is nice is that the 0th order so it looks always as an Hamiltonian of a 3-level atom, but in fact if you combine the two ground state with the proper coefficient, you find out that you have one coupled state to the excited state and one non-coupled state, and so you can drop it. And so this is the Hamiltonian of a 2-level system, and a 2-level system you know how to compute everything. And then when you have the 0th order solution, then you just have to add the first order Hamiltonian, which is fantastically simple because you have zeros almost everywhere, and you have just two. So it is rather strange. Usually you have you use perturbation theory when your perturbation Hamiltonian is off a diagonal. But here it is on diagonal, but it doesn't matter. So you just have now to turn the crank and look for a solution where you have the 0th order plus the first order, and from that you just continue. Are you interested in it, or just yes? Okay. So so the 0th order, you find out that you have stationary population at the 0th order, which are plus minus squared divided by 4. And I use a shortcut, plus squared plus. So this is just the usual 2-level atom. In fact, It is just that here I have only one ground state which is coupled, so I can compute the population for the coupled, the excited state, which is the total omega, which is here. This is the usual formula. And when I split again the coupled state in the two original states, then it turns out that the omega squared that was here just becomes omega plus or omega minus, depending on which one I am considering. And so now I have the first order force, which is just with the same argument that to reach this level, you need to absorb one photon from this laser, and to reach this level, you need to absorb a photon from this laser. Then the spontaneous emission from these levels is also the absorption rate from the same levels. In fact, in the 1D geometry, the stimulated emission doesn't play any role, because if you absorb a photon and you have a stimulated emission, it is in the same direction as the absorbed photon, so it cancels out. So you just have for the friction force and the restoring force, you just have to compute something which KL gamma, and you have the first order. You have to compute the correction, the first order correction for the populations, and you turn the crank. It's a bit tiring, and then the formula will fit in this space, but not much more. So the first prefactor is the same as usual, and you have the same for delta squared plus 2 squared, and you have a first term which is omega squared. Fantastic. This is just what you would have guessed, but you have a correction, an awful correction. Okay, so here you see that you have a correction that cancels if the total Rabi frequency is equal to 2 gamma. Okay, why? I don't know. What is interesting is to evaluate the order of magnitude of this quantity, because so if it is just neglectable, it's okay, you will just drop it. But obviously, so the first calculation, so numerical application, is just to consider that omega is on the same order, is gamma, and that the detuning is the usual one for magneto-optical trap, which means 2 gamma, which means that this is almost low saturation, because you find that S is about 1 divided by 16, so it is and at that point you find out that this correction gives you an increase of only 4% in the friction coefficient. So, okay, you can neglect it. But if you go to the other limit, which is the limit of very high intensities, so now I switch to the case where omega is much larger than delta and gamma, and also I assume that omega plus equal to omega minus. And so if you just look at what happens, it shows that you have your alpha coefficient that goes to 0. So, okay, it always goes to 0. But now it goes to 0 as omega to the minus 4 power instead of something like omega minus 2 power, which is the usual term if you forget the correction. Here you have omega 2 divided by omega 2 squared. And so this means that in the high saturation regime, you have to take into account this correction if you want to make something properly. Okay. So everything, yes, okay. I will maybe have to rewrite something, but anyhow. So in the last, yes, 25 minutes, okay. I will switch to the second part of this, and I will consider the limit temperature in the low saturation regime. Okay, so I have the force that is minus alpha v. So as I am in 1D, I just forget the vectors. And for the moment, I will forget the restoring force. So it's the molasses and not the mott. And so if you just consider this force, then the consequence is obvious. You have a damping of the velocity, and which means that the velocity will go to 0 in a finite time. And this is somehow puzzling. And why do we find that the velocity can go to 0? It is just because we have considered here only this was the mean force. And in the calculation, we have introduced a force operator, and then we have taken the average of the force operator. And this was the mean force. But this force operator has some fluctuations. And for instance, if you consider the coupling with the vacuum, from the atom with the vacuum, this is obviously non-zero, even if the average value of the same quantity, because of the symmetry of emission, spontaneous emission can be can go in either direction with the same probability. So now we have to make all the calculations, but taking into account the fluctuating part of the force, and we will do that following the path of the Brownian motion. So, in fact, we will consider that you have, no, in one dimension I do not have any. So the derivative of the momentum for the atoms, for an atom, one specific atom, is just minus gamma p. So this was the damping force. But you now have to take into account random fluctuating instantaneous so obviously this, so I write it in momentum instead of in velocity, but you see immediately that you have the link between gamma and alpha like that. So the random force is assumed to be 0 on average, but you can have some correlation between the force at two different time. So this is by definition f the t prime, and this quantity is a priori non-zero. If you have a stationary problem, instead of considering t and t prime, you can have only f of 0 and f of t prime minus t, because the problem is time invariant, and so t prime, you just, what is relevant is only the splitting between the two times that you are considering. And if now you consider a time interval where you have the difference between the two internal times, which is larger or on the order of the internal time to reach the steady state internal state, then you can say that on that time scale, for this time scale, the correlation just drop to 0. If this, because your atom has just made a lot of emissions, absorption emissions, and so the correlation force just lose any memory of what happens before. And for our purpose, we are interested in the external variables. And so we are interested in times which are much larger than the internal time. And so for our purpose, which is not for all the purposes, you can consider that this quantity just becomes a delta function. with this coefficient. So don't ask me why they put a factor of 2 here. They put a factor of 2 here. I did not invent this notation, so okay. So these are only just tricks, old tricks, and they allow us to do a lot of things. Okay, so now, what are we doing? What is the next step? In fact, the next step is to integrate formally this equation. And if you integrate formally this expression, you just end up with the momentum at a time t is just the momentum at time t equals 0, which is damped with a gamma t. And you have the contribution of each kick in the past. So f of t prime. But these kicks have been damped also, and you have a damping factor which is t minus t prime. So this is just the formal integration of this expression. And you see that, so this is just the initial momentum that is damped. And just assume that you have only one kick at a given time t prime. Then this kick changes the momentum by f of t prime. But to survive until the time t, it is damped with the exponential gamma t minus t prime. Okay? So if now you just compute the mean value of the momentum, then the mean value of the momentum is the mean value of that, which is obviously itself. And here you take the mean value of the force, which is 0. And so the mean value of the momentum is just simply the evolution of the damped initial motion. But this is not what we are interested in. What we are interested in the spread. So it is delta p squared, and delta p squared is p of t minus mean value p of t squared and the mean value of that. And so you turn the crank, so this term disappeared, so you have just this term squared, but this term is an integral. So in fact, when it is squared, you have a double sum on t prime and t second. And in fact, you will find something like a mean value of f of t prime, f of t second. And if you go to the end, you find out that this is just d divided by gamma 1 minus which tells you that now if you wait long enough, so this term disappeared, and you end up with a temperature which is just 1/2 of kBt, which is 1/2 of delta p squared divided by m. And you find out that kBt is just d divided by alpha. Okay. So that's very nice, but we don't know what is D. So now we have to play a little bit to have some hints to say, okay, D is equal to, and yes. Okay. So it is the diffusion in and in fact I will look what happens for short times. So this means that I have to consider times obviously that are much larger than the internal timescale, because otherwise I can say nothing. But I am also interested in times that are much lower than the external time. And if I just I assume that the time is also smaller than gamma minus 1, then for these short times I can approximate the relation that is here just by 2d times t. Okay, nice. Now I will say that for each spontaneous photon, I have a momentum kick to the atom, and so the momentum of the atom change by a quantity which is h bar, the k of the laser, so it is either plus or minus, and you have the spontaneous photon, which is emitted. And so once again, the stimulated emission plays no role because of the simple 1D geometry. And we can say that these processes, because in fact we have here, this one can be plus or minus. We have random processes that goes on with a probability by unit of time, which is just related to the population of the excited plus level if the photon is absorbed in the plus beam, or minus pi minus gamma in the other beam. So I can say at that point that my atom, for a time long enough but short enough, this delta p is just pi plus minus pi minus gamma t h bar k, so kl, because the spontaneous emission is with the same probability in the plus and the minus direction, and so this mean value is 0. Okay, but if now I look at the squared value of the kick, then I have something which is h bar KL squared plus h bar, squared, spontaneous squared. And here you have a plus or minus 2KL K spontaneous. And what we are interested in is the mean value of that. And so in the mean value, this one remains the same. This one becomes the mean value. And this one just drops out because the mean value of K spontaneous is the same in the two directions. So in the 1D problem, if you consider that you have a dipole which oscillates like that, you all know that the field radiates like that. And it turns out that the mean value of the spontaneous emitted photon is just 2/5 of the K laser. So this is just for this contribution. And now so this is the mean change of squared momenta for each spontaneous photon. And now you just have to count how many photons are exchanged. And so during the time t, you exchange a number of photons, which is in average equal to pi plus pi minus times gamma t. But this is an average number of photons. And as almost always, when you have a number of events, this number is not exactly determined, but it is a discrete random process, and you will end up with a Poisson distribution. And as a result, you will have the variance of this number is just the mean value of this number. Okay. So we have finished, almost. And just in time, yes? Fantastic. Okay, so now we want just to identify this expression with what we can guess from our feeling of this random process going up. And in fact, you have a first term which is just related to the fluctuation of absorbed photons, and you have another contribution which is related h bar squared k squared, and you have, and this is the fact that the direction of the spontaneous photon is random, and so now you have just the number of events and the mean value of. So this is the fluctuation, is related to the fluctuation of the number of photons, of absorbed photons. So this is, in fact, the variance of n. And this is the randomness of the random direction of the spontaneous photon. So, again, in the low saturation, we have pi plus equal pi minus equal omega 1 squared divided by 4 delta squared plus gamma squared. And so you just have d, which is gamma omega 1 squared divided by 4 delta squared plus gamma squared. And you have a ugly 7/5 of h bar squared k squared. So very often in the literature you can find something else here, because if you consider a 3D problem, then you can write that the spontaneous emitted photon is just 1/3 in any direction, and so it changed a little. You will not find again, if you change 2/5 be in 1/3, you will find here 4/3 instead of that. And so the other quantity I just rewrite, but you have already it in the notes, is just gamma omega 1 squared divided by delta squared plus gamma squared divided by 4 squared and h bar k squared. And you end up with kBt. So I put quotes because the thermal aspect of the interaction is not so obvious. So it is by definition the delta p squared, which was what was written here, d divided by alpha, and it turns out to be h bar gamma. So I have 7 divided by 20, you can drop it, and you have a delta squared divided by delta 2 divided by 4, and you have a delta and a gamma. So if you look at this quantity, you find that it is minimum for delta equal gamma divided by 2, and it is equal to 1 in this case. So very often in books for a 3D problem you will find simply kBt in 3D, which is assumed. So the minimum value, which is just h bar gamma divided by 2. So probably here I have 7 divided by 20, which is 1/3, but it is almost the same. Okay, so no, I stop here. Thank you. Yes?
What do you mean when you say the temperature isn't obvious?
It is a full... in fact, the temperature is properly defined only in a thermodynamic equilibrium. Here you have atoms that are in equilibrium but with light, with the laser beams. And I'm not sure that all the thermodynamics will be fulfilled. And so obviously when this notion of temperature has been introduced, it was a problem because there was a fight between the classical cryogenic method that allows to go to maybe 100 millikelvins, and this new technique, 1 millikelvin, sorry. So, and this new cooling method, and so to compare the two possible methods, you have to put some figures, and the natural figure is the temperature. But if you look at the distribution, the velocity distribution you can find in a MOT, in fact the fact that the force decreases for large velocities means that you do not have the usual Gaussian wings for the large velocities. So this temperature is, for historical reason, a natural quantity to characterize the mean kinetic energy, but it is not a temperature in the thermodynamical sense. That's all. But you can talk for hours and discuss this. So, yes.
The derivation until the last one was in 1D?
Yes, everything was a 1D.
Next question.
Thank you.